SDN is an approach that enables the network to be intelligently and centrally controlled to improve network performance. SDN separates routing control from data forwarding. Its control plane consists of one or more SDN controllers where the whole intelligence is incorporated. However, centralized control suffers from scalability and reliability issues. Distributed SDN is proposed to balance centralized and distributed control over the network. A distributed SDN network is composed of a set of subnetworks or domains, each managed by an independent SDN controller. Controllers synchronize with each other to maintain a logically centralized network view. Notwithstanding, distributed SDN networks can only afford partial inter-controller synchronizations since complete synchronization is costly. An example of a task directly affected by controller synchronizations is routing. For instance, the controller CO, with its current view of the network from the last synchronization, builds routing paths that traverse the domains of other controllers, C1, C2, and C3. Due to the dynamicity of networks, the network view of controller CO may not be synchronized with the current status of the network. Then, the path is built with an outdated network view. The question of how controllers should be synchronized with each other to maximize routing performance is still a problem to be researched. We face the controller synchronization problem by using reinforcement learning to learn the best synchronization action under a given desynchronization state. The goal is to maximize the long-term reward, which in our case is the difference between the real average path cost, APC, and the APC computed by the source controller, this is, with its network view. Each state is represented by a vector sized with the number of domains in the network -1. This is one variable per each domain, except the source controller. These variables indicate the number of time slots elapsed since the source controller was last synchronized with each of the other controllers. We assume the maximum desynchronization time slots to be the duration of simulation, as each variable takes values in the interval 0, t. The size of the state space is computed by the equation shown. Each action indicates the controller to which the source controller will synchronize with and is denoted by a vector of binary entries. One indicates the decision to synchronize with the corresponding domain. Since source controller only synchronize with one controller at each time slot, the size of the action space is the number of network domains. The immediate reward at each time step is computed as the distance or difference between the APC of constructed paths computed by the source controller, with its current network view, and the real APC calculated with the actual link weights. We implement the environment as a discrete event simulation where time is splitted into time slots. The events considered in the simulation are change of weights in links and synchronization of controllers. Experiments. We trained 2 off-policy and 2 on-policy agents in 2 variations of our environment. The normal has more than 4 million state action pairs while the expanded has more than 10 million. Agents and results. Souza Lambda converged after episode 150 in the normal environment while it did after episode 200 in the expanded one. Q-learning agent converged before episode 200 in the normal environment while it did after episode 300 in the expanded one. Q-learning and Souza Lambda performances are close in both environments, being Souza Lambda slightly better with an average reward of -146 in the expanded environment. A2C agent got an average reward of -726.55 in the normal environment and -302.34 in the expanded one. ASA agent, in both normal and expanded environments, converged approximately at episode 200. Its reward was much higher in the expanded environment. ASA performed much better than A2C, showing an average reward of -98 after convergence in the expanded environment. Conclusion. The relatively small quantity of state action pairs in the normal environment allowed the agents to reach the convergence quickly. The implemented reward function, state and action spaces were appropriate for achieving our objective, reducing the difference between real APC and the APC calculated by source controller. Tests on the expanded environment show that the agents obtained higher rewards since such environment considers additional actions, i.e., synchronize with more than one controller at a time, which led to learning a better policy. Q-learning obtained the best performance in the normal environment while ASA was the best in the expanded one.